Our next speaker is someone I've known for a long time, and I know a little bit about his technological area. I used to run the Pennsylvania Nanomaterials Commercialization Center for about 5 or 6 years. So Matt Kim is the founder and president of Quanterra, a microelectronics research and development company that specializes in nano-engineered devices for photonic telecommunications and wireless applications. He's an expert in the crystal growth for photonic applications and the microelectronic fabrication and testing of semiconductor devices. He has been awarded numerous innovative research grants and contracts from the Department of Defense and the National Science Foundation for the development of cutting-edge lasers, transistors, and integrated electronics. Dr. Kim is presently the chairman of the Arizona Nanotechnology Cluster, which provides many educational resources for students at the middle and high school and college levels, as well as many programs for the general public. In 2006, Dr. Kim was recognized at the Arizona Technology Council's Governor's Celebration of Innovation with a Chairman's Award for his contributions in technology in Arizona. In the past, Dr. Kim co-founded MicroLink Devices, served as a principal staff scientist at Motorola's Corporate Research Laboratory for prototyping high-speed transistors, microwave devices, and optical devices, and was a senior scientist at Bandgap Technology Corporation. Dr. Kim received his PhD in physics from the University of Illinois at Urbana-Champaign and has a BS in engineering physics from Cornell University. Dr. Kim?
It's a pleasure being here, and what I have is, I brought a poster, but I can see the screen really does quite a bit to my poster, but this is real, okay? And that's Memorex, so just, but the reason why I show this poster or this image is because this inspires me. It inspires me when you understand the nuances of this, but what this is called a scanning tunneling micrograph image of what we call highly oriented pyrolytic graphite. And this is also kind of nice because it's done by a company in Phoenix, Nanoscience Instruments, just about a mile from my lab. So whenever I need a good image, I go to them. But what this shows you, it shows you carbon. And it shows you a plane of carbon atoms. And I'll discuss this a little bit in detail. But one of the things that's very interesting about carbon is ubiquitous. It forms bonds with everything. It forms bonds with all sorts of things. So the story of life is based in carbon. We're carbon-based life forms. But before we get on to this a little bit, you have to know the history of carbon. So carbon has a very auspicious history. A long time ago when the universe was formed, there was just hydrogen and helium. That was it. And then gravity took effect. And when gravity took effect, it started compressing the hydrogen and the helium, but there was a problem. Physicists knew to make carbon was not a normal process. No. To make carbon, you have to be in a star. So the hydrogen and helium formed into a star, and that star, under immense pressure and temperature, a process occurred. It's almost a miracle. It's called a triple alpha process. And what that is, it means 3 helium-4 nuclei have to simultaneously merge to form carbon. Now, if you're a scientist, a 3-particle simultaneous interaction the probability is almost 0. It's almost 0. However, if you have enough helium in hydrogen, and you have immense pressure, and then you have about 100 million degrees Kelvin, okay? 100, you don't get that everywhere. Then you can make carbon. So all the carbon that's here is from that stellar process, which is a very auspicious process. Now, what's interesting about carbon is this. If you've taken organic chemistry is the study of how carbon and hydrogen bind to form molecules. Carbon forms the most molecules of everything. But carbon also forms inorganic forms, like diamond, graphite. Diamond the hardest substance known to man. Graphite, one of the softest substances known to man. Both are carbon forms. They're called allotropes. But what's interesting is if you want to look where nanotechnology or bioscience will go, it's where you can link it, and the linkage is carbon, because carbon can be in many nanoforms, and carbon can be in many organic forms. And so as science progresses, you'll start seeing these linkages bigger and bigger, because that's really the key. How do you engineer the carbon? How do you engineer the organic molecules like pharmaceutical companies do, biologists do? But what's really interesting is why is the carbon atom so important? Well, it's not just a carbon atom, it's all atoms. You see, the atom, there are 92 atoms, roughly, naturally occurring, they say. And they make up all the universe. And the reason why they can make up all the universe is because the atom, as an instrument or an entity, controls the electron as precisely as the electron can be controlled. All right? There's no other thing anywhere that controls the electron. And when you can control the electron dominates everything we do. Electrons and photons dominate almost every biological process. Because the atoms can dominate the electron so precisely, they have infinite control of the electron. And what that means is you can make the electron do what you want. Now, how do they control it? Well, there's a funny aspect of electrons is when they get confined, they start doing funny things. And what the electron happens is in the atom, you're not going to like this term, but it's called a zero-dimensional particle. And the reason why we call it a zero-dimensional particle is because the electron in the atom has no degrees of freedom. It can't go in X, Y, and Z. It's stuck there. And when it's stuck there, now you get this thing, and the atom obeys what we humans call quantum mechanics. But that doesn't matter. So what do we do in nanotechnology? Well, what we want to do in nanotechnology is we don't want to make things that do the work of the 92 naturally occurring atoms. That's already been done. Nature did that for us, and it did it in the stellar furnaces of the stars. What we want to do is we look at the world around us, and we live in a very narrow range of temperatures, very narrow range of pressures, and you have very humanistic needs. One humanistic need is color. When you look at TV sets, right, or when you look at light, there's certain colors that make us feel good or whatever, but that's a humanistic need. Nature doesn't have to make those colors. The only reason why our eyes are sensitive to the spectrum that we see is because the sun is there. If we lived on a different planet, it'd probably be different. So when you look at that, you say, well, okay, how do I do this? And you say, well, I have the atom as my inspiration, and what I want to do is make things that mimic the atom, because then I get the bricks to build structures in our world. You see, if you look at everything, nature makes a lot of things, but you don't see nature making the exact same thing, like bolts, right? You know, you go to Ace Hardware, you can get bolts everywhere, and they're the same. Well, as nanoengineering, that's what we have to do, is we have to make substances that are like bricks or bolts that we can then build together to make structures that are useful for man. And so this is what that image shows you. And this is why this image inspires me, because if you look at the advent of nanotechnology, it really started, even though Richard Feynman gave reference in the 50s, it really started in the 80s because this scanning tunneling microscope was invented by Benedict Rower in IBM Zurich. It was the first image of the atom, but secondly, these IBM scientists were very good. They then, another group of IBM scientists, then could move atoms, move single atoms, manipulate atoms. And when you can image and manipulate, that was the advent of nanotechnology. Because now we know we could build structures atom by atom, organically, top down, or bottom up, doesn't matter, but you could do this. And what this image shows you is this. What you see here is, if you look over here, you see graphene. So this image should actually mimic that. But it doesn't. You know why? Because this image tells you a deeper story. You see, those bumps there aren't actually the image of the atoms. They're the images of where the electrons are. So actually, you should see 3 more bumps, but you don't. But what this structure shows you, it shows you a beautiful picture of on the surface of carbon that I'm getting electrons controlled, just like the atom in carbon or in any. However, this kind of controlling, we call this a 2-dimensional kind of controlling, isn't as precise as the 92 elemental atoms. It's not that precise, but it doesn't have to be because we're not making the universe. We're making structures that are useful for medicine, for telecommunications, for structural things. But that's what this shows. And when you can do this, then you start realizing now that by taking these electrons and putting them into these low-dimensional structures, remember the atom is a 0. It's what we call a quasi-zero dimensional. But when you do that, now you can control the electrons, make them do your bidding, and you can then make things that are replicable, right? We got to make things that are replicable because you need bricks for society, and then we can actually make certain structures that are useful. And what people are doing in medicine now is they're actually taking things, and in medicine there's 2 areas. One's called diagnostic, one's called therapeutics. And they're using these nanoforms to actually engineer ways of doing drugs that are in therapeutics called targeted drug delivery, where you can actually put a very toxic drug, severely toxic drug, but you put it, you nanoparticleize that drug form, and then you put it in a container maybe in something like a buckyball or whatever. And actually there are companies that are doing, there's a company in Phoenix, Celgene. They actually do targeted drug delivery where they take a very toxic drug, methotrexate, coat it, and then it can be delivered into the body with efficacy. You see, most of these chemotherapeutic therapies are very toxic. And so that's where things are going. But this is really what we're doing. And if you look at the mantra of nanotechnology or whatever, it's control, control, control. We have to control things. And when you control the electrons, just like you do in the atoms, now you have something. So when you go home tonight, what you do is look up at the star, and you'll see those are the furnaces of where carbon came from. 20% of you is probably of carbon. And that's what we actually use now as a template for engineering all these types of new discoveries in, I believe, in medicine and all sorts of things. Thank you.